Cern scientists may have discovered a brand new natural force, and it's mysterious. Physicists believe that they may have been seeing some new undiscovered physics come into play, but what exactly is going on? The Large Hadron Collider, or LHC, is the world's largest and most powerful particle accelerator located near Geneva, Switzerland. It's designed to study the fundamental properties of matter and the forces that hold them together. The LHC has been operating for over a decade now, and during that time it's made some groundbreaking discoveries, including the confirmation of the that's responsible for giving other particles mass. But despite all of its success, the LHC has also been the subject of controversy and conspiracy theories. Some people have even suggested that the LHC could create a black hole that would destroy the planet, but of course those fears were unfounded, and the LHC has been operating safely and without incident for years. However, that all changed recently when scientists at Cern made an announcement that has sent shockwaves through the scientific community. They revealed that after turning on the LHC, they had noticed some strange readings that they couldn't explain. Specifically, they'd observed an excess of events that involved the production of muons, a type of subatomic particle that's similar to an electron but much heavier. To understand why this is significant, we need to first understand a little bit more about muons. Muons are produced when cosmic rays, which are high-energy particles that come from space, collide with the Earth's atmosphere. These collisions cause a chain reaction that produces a shower of subatomic particles, including muons. Muons are very unstable and only exist for a fraction of a second before decaying into other particles. Muons are important in the study of particle physics because they can be used to study the properties of other particles. For example, the mass of the muon is very similar to the mass of the electron, which is one of the most common and well-studied subatomic particles. Studying the differences between muons and electrons can help scientists understand the fundamental properties of matter. See, the thing is, there have never been any magnetic monopoles that can be detected, even the strongest magnetic field that's ever been measured anywhere in the literal universe. Despite the presence of these hypothetical particles being predicted by a number of calculations of potential phenomena that defy the predictions of the standard model of particle physics, more than a century of research has not turned up any proof that they do. Every sort of magnet that we're aware of has at least two poles, usually referred to as a north pole and a south pole, and these poles contain opposing magnetic charges. And on the other hand, the presence of magnetic monopoles, which are particles with only a north or south pole, is hypothesized by some theories of the universe. For instance, the existence of magnetic monopoles would account for the quantization of electrical charge, which means that it comes in packets of a minimum size. Magnetic monopoles have been sought after for the larger part of the past century, but neither have been found in space nor in the collisions of particles that take place in particle colliders. But while Cern researchers were searching for these monopoles, their investigations yielded a completely unexpected outcome that astounded scientists across the globe. So when scientists at Cern noticed an excess of muons, it was quite puzzling. They'd expected to see some muons, of course, but the number they observed was much higher than they had predicted. This led them to speculate that there might have been some new physics at play, something that we haven't yet discovered. At the time of making this video, the Large Hadron Collider uses 6.5 TeV of beam energy. Trillions of particles circle the collider's 27-kilometer-long tunnel 11,245 times each second at this energy. The particles are accelerated through a network of interconnecting linear and circular accelerators before entering the LHC. They're sent on to the next accelerator chain as soon as they reach the maximum speed that one can produce. The particles would follow their momentum in a straight path and drift away in the absence of any other force. More than 50 different types of magnets are required to move them around complex routes without losing speed. On the LHC, they really only use electromagnets, strong 8.3 Tesla magnetic fields produced by the main dipoles. This is a huge number. Just for perspective, that's 100,000 times greater than the Earth's magnetic field. The excess of muons was observed during a specific experiment called the LHCb experiment, which is one of the four main experiments taking place at the LHC. The purpose of the LHCb experiment is to study the differences between matter and antimatter. Antimatter is a type of matter that has the same properties as normal matter, but with opposite charges. When matter and antimatter come into contact, they annihilate each other, releasing a large amount of energy. One of the goals of the LHCb experiment is to study the decay of the particle called the B meson. The B meson is a subatomic particle that's composed of a bottom quark and another quark. The B meson is unstable and decays into other particles after a short period of time. By studying the way that the B meson decays, scientists can learn more about the fundamental properties of matter. There are a few possible explanations for this strange phenomenon. One possibility is that the LHC is producing more muons than we previously thought. This could be due to some kind of unexpected interaction between the LHC and the surrounding environment. For example, it's possible that the LHC is producing more muons because of interactions with cosmic rays or other sources of radiation. Another possibility is that the excess of muons is the result of new physics that we haven't yet discovered. Some scientists have speculated that the excess of muons could be a sign of the existence of new particles, such as sterile neutrinos, which are theoretical particles that don't interact with matter in the same way as other particles. A third possibility is that the excess of muons is the result of a statistical fluke. Because the LHC is producing a large number of particles, there's always the possibility that some experiments will produce unusual results simply by chance. So what does all of this mean? Well, at this point, it's too early to say for sure. The excess of muons could be a sign of new physics that we haven't yet discovered, or it could be a statistical anomaly that will be explained by further research. But either way, it's a significant finding that has the potential to advance our understanding of the fundamental properties of matter. It's also worth noting that this discovery is a testament to the power of the LHC and the incredible work that's being done by scientists at Cern. The LHC is an incredibly complex machine that's capable of producing particles with energies that are higher than any other particle accelerator in the world. And the fact that scientists at Cern were able to notice this excess of muons is a testament to their skill and dedication. Oh, but it doesn't end there. On July the 7th, just a few days after the LHC was reactivated, scientists were searching for monopoles created by the Schwinger effect, a hypothetical phenomena whereby very strong magnetic fields could spontaneously form magnetic particles and their antiparticles. The group used the strongest magnetic field ever recorded. When two lead particle beams collided at the LHC at extremely high speeds, a magnetic field was created. It measured around 1016 Tesla. That's about 100,000 times stronger than the magnetic field from a magnetar, a highly magnetized neutron star. The number of the massive monopoles we can theoretically make increases with the strength of the magnetic field. Yet, the absence of monopoles led the researchers to set their first firm limits on the mass of these particles. They must have a mass that is at least 70 times that of a proton. Yet following these tests, the company issued a somewhat odd statement. They claimed to have found a break that had appeared on the Earth's magnetic field, and that this split had been open for 14 hours. Social media users subsequently reposted the post, which led some people to believe that Cern was creating some sort of doorway for evil to go through of sorts. Despite the fact that a hole in the Earth's magnetic field did open, scientists believe there is no cause for alarm. However, the researchers did note that even with the breach open, solar winds of a certain intensity can still travel through. I mean, the magnetic field literally keeps our planet habitable by preventing the ozone layer from being destroyed by the harmful winds of the sun. But how did this crack even happen? It turns out that a co-rotating interaction region from the Sun is what produced this magnetic field breach, an uncommon occurrence. Large-scale plasma structures known as CIR are created when fast-moving and slow-moving streams of solar wind collide in the heliosphere's low and intermediate latitudes. The area surrounding the Sun that houses the solar magnetic field and solar winds is known as the heliosphere. Co-rotating interaction regions drive coronal mass ejections, or CMEs, away from the Sun. They may have shock waves trapped in compressed magnetic fields, causing erratic space weather that we observe as stunning aurora. This one caused a long-lasting G1 geomagnetic storm on July the 7th when it struck the US magnetic field early in the morning. Because Earth's magnetic field fissures occur frequently and serves as a shield to keep us safe from solar storms, which are somewhat rare, researchers believe there is no need to panic.